so, so, so the lecture today is going to be on cross-validation, which is if you've not seen cross-validation before, let's make sure that's muted. Great. So if you've not seen cross-validation before, this is possibly one of the most possibly one of the most important concepts you've heard in the class. So this is the idea about how to evaluate so how well the models you're using are working. So it's the idea of we're going to take our data, we're going to split it in two parts, we're going to train it on one part, and we're going to evaluate on the other part, right? So I'm just curious. So as a kind of a show of hands, you can do hands or yes, no, or something. How many people have heard of cross-validation before versus having not heard it? So a hand would be a yes, or a yes would be a yes, or a no would be a no. So, okay, so I'm, yeah. So I've seen of, so okay, a few people fast forwarded. So it seems like a few people have heard this idea before, but so most of you have not, right? So we've talked about, I've alluded to some ideas you may have seen in like statistics, where you come up with a model and then you try and you assume some probability distribution, and you can do like some sort of like hypothesis test about so like how likely is this model so it's supposed to be different from the model, I suppose. And so this is, I'm not going to get into this explanation. It's not not really that related, but this is the cross-validation is a very different view of how to evaluate if a model is working. So there are often ways when you can, well, so they're often used in different scenarios. Cross-validation, I mean, the idea is not that new. It's older than 20, 30 years ago, but like hypothesis testing goes back like over 100 years. And in some fields of study, they are kind of, don't think of cross-validation as being the way to evaluate how well they're doing. And we'll try and discuss a little bit about these, about when you can use cross-validation, when you can't. Basically, when you have lots of data, it makes sense to use cross-validation. And so this is really part of the core way that things have changed in the last 10 or 15 years in machine learning and data mining and stuff, where we're now in this world where we have often access to this large amounts of data, and we can use part of that data, hold that out to do do like the evaluation. Whereas olden days, when statistics was invented in the 1900s, every data point that you had to hand gather, right? There's if Fisher is doing an experiment with tea, or Mendel is looking at some flowers, they need to personally often conduct the experiment to get each single one of those data points. Now you automate it, and the computer is doing this stuff for you. And so you can get thousands, hundreds of thousands of data points. And this kind of opens up your eyes to different ways of working with things. So this is a really important conceptual shift in how data analysis is done in the more recent world dominated by machine learning and data mining. It's not to say it's the only way that's done. There's still kind of plenty of other things done in statistics, and there's a place for that. But cross-validation is kind of this kind of newer paradigm. So okay, so that's the point. That's the intro of this lecture. A couple of you still have things up in the participants Mike has a hand up. If you do have a question, feel free to ask. Okay, great. So let's, before we get into the lecture, let's just look quickly at the schedule. So homework 2 is due today. So hopefully you got a chance to play with Python and NumPy to do the linear algebra part at the end. If not, I suggest you do that. We're going to start using it in slightly more complex ways, and I don't want that to be challenging. And the first question hopefully made you think a little bit. The homework 3 will be on basically linear regression, which is this section, and gradient descent. We'll post that within the next week. It's close to being ready to be posted. And so once it's posted, you should be able to start on the linear regression part of it. Other thing is quiz 3 is going to be on Monday. Quiz 3 will cover the last lecture of linear algebra. So there are a couple of parts in the inverse and like orthogonality that we did not cover on the previous quiz. So I might ask questions on those. That's part of the things I want to review. And then the rest is going to be on linear algebra on linear regression up through this lecture on cross-validation. The lecture on Monday is going, I kind of built a little slack into the schedule. In a typical semester, this is the last day before you have a fall break. There's no fall break this year, but I left the slack in there. And so I think we went a little bit faster than I wanted to on Monday's lecture. So I'll probably start by reviewing stuff in linear regression and polynomial regression in there. And either after that, either I can take questions about stuff that might be on the quiz, or I can talk more about other forms of nonlinear regression in that space. So okay. So any general questions on the schedule? So good. So on the next quiz 3, you will again get a cheat sheet. Should be one side of one page. Again, you'll turn it in, and someone asked me to revote, and I forgot to. Did people really want me to revote? I think we'll probably plan. Okay. I think we'll probably plan to make it worth 5 extra points toward your grade, but not to go above 100. So yeah. So there's a question. Go ahead.
About the cheat sheet, I typically end up making them more than one page, but typically I'll condense some of the things that I usually kind of like forget typically into more of a one-page format. Are you looking for are you actually looking through the cheat sheet for what we're talking about? Should I try and populate that with the majority of the ideas, or what'll help me the most?
So yeah, so the idea of this is the reason I have one page. I'll ask you to turn in one page into Canvas. I'm not using one of these kind of questionable ProctorU things, so I'm not checking on you what you're actually doing. But I suggest one page of the things you think are going to be most useful on this topic. I say one page instead of 2 or 3 or 4 because I'd like you to focus on the very core things and trying to think about what was the most important thing. You're welcome to take more notes if you want to. Yeah, so I think I say typically you can use anything that's linked off the web page, basically the book or the notes on there. Yeah, these quizzes are basically meant to be open book. I don't want you searching on Google for stuff, and so I'm not enforcing if you're looking at your other notes. But I want you to make one page and to upload one page. I think one page is about the right size for distilling the core ideas in the material. You're kind of welcome to make your own notes and your study guides with more pages if you want to. if something magical happens and we can have an in-person final, then my plan would be to allow you to have basically 6 pages you could bring in to the final, which would be one page per quiz. Okay, so that's kind of the idea. I'm pretty sure we're not going to have in-person finals, so it's probably going to be more the same in some way or the other. But hopefully that gives you an insight into what I'm asking for. Okay, great. So okay, so let's get on with the lecture. So cross-validation. So okay, so where did we leave off last time? And we had left off in particular where we had this this data, which was x and y. And let's just stick with the simple case here for now, that x, yeah, so x is going to be a subset of n by d, so n data points in d dimensions, and we'll say that here we'll set, say, d equals to 1. Okay, so we'll, just for the simple example, we'll say d is equal to 1, and then y is going to be in our n. So this is these real values that we're trying to predict, right? So each xi in x corresponds with a yi in, you know, xi is an element of x, and we're trying to build some model, right? So the goal is then to build some model m alpha, which will take this and will give us this this yi hat. We want yi hat to be close to these yi's, right? And we talked about, we're going to measure this with the sum of the squared errors, where like we're going to get a, so residual, which is going to be a y hat minus yi, and we want the sum of these squared residuals, right? This will be like our sum of squared errors to be as small as possible, right? So we want to find a model that's as small as possible, okay? And then we explained last lecture that we could build, instead of a linear model, right? Instead of a linear model, we could build we could try and build a polynomial model, okay? So a polynomial model, okay, that would be m of alpha of x to the power p would be something that would be a sum of j equals 0 up to p of alpha j x to the power p. Remember, and x to the power 0 is going to be a 1, right? So so it's going to be a constant for any value x, right? So this is the polynomial model, right? And so if you expand this out, it's like alpha 0. This would be alpha 0 plus alpha 1 x plus alpha 2 x squared, you know, up to the pth power of x, right? So this is a polynomial model. And then I eventually showed you on Python in NumPy how we can calculate these fits. And we got these pictures who I've shown here at the bottom, where this first one is this linear model, right? And that's only the first 2 terms here, right? So if I just look at the first 2 terms, alpha 0, which is an offset, right? So alpha 0 was the offset, and then there's some slope of the line. But then if I went up to degree 2 instead, right? If I went up to degree 2, then I'm going to get a curve that looks like this. It's going to have, again, some sort of offset, but then it's going to have this, I'm fitting a polynomial function through here instead. So this is like an upside down parabola, right? A 2-degree polynomial function has to be a parabola that goes up and then down, or it starts up and goes down and then comes back up. Those are the two options. Some sort of parabola. All polynomial models are some form of parabola. And then you could fit a third degree polynomial that I've shown on the right there, or a fourth degree or fifth degree, and up to an eighth degree. Okay, and in this picture for the eighth degree, okay, I've managed to get this line so it goes through every single one of these data points, right? But it's doing something kind of weird here, right? It's got this weird bump that goes higher than any data point I see. And then it ends up small again, even though you kind of see this general trend of things increasing, right? The general trend is things are increasing. But I decide that this model says, well, once you get past the end of my data, it's probably going down to zero. It's an even degree polynomial, which means if it starts at negative value, it has to end at a negative value, right? Where odd one starts negative, it ends positive, in some way. So this is eighth degree polynomial. It has to do this, but it managed to go through every single one of these data points. So this seems great as a fit onto the data, but it's probably overfit, okay? So there's probably this term that is a common term. I'm not sure if this is the, I'll mention some very recent developments in our understanding this the last 2 years about cross-validation and overfitting. But this would traditionally be said, this is overfitting of the data. My model goes through every single one of the data points, but this is probably not as good. This is probably not of a good as a model as these other ones, right? So does anyone want to volunteer in the chat? Why would this not be as good of a model? Which model do you think is the best here? Of the 6 pictures I have, which one do you think is the best, or why is the one with degree 8 probably not the best model? Just so okay, great. So someone says the second, because they think it will do the best at predicting new points. Someone else says the linear one, which is predicting this upward trend. So yeah, so good. So and so someone else says too the second model. Yeah. So I would say possibly the first or the second one are probably the best fits. It's if you believe that there's a general upward trend and you think that the data is saying that and you think that's likely to continue, well, then the first model is going to do that, where the second one is not. It's a parabola, so it has to go down again. And then the second model is doing good because it's fitting the data better than the first model. If I could calculate the residual on these, right? Remember, I can calculate this sum of squared errors on the residual, and the second model will clearly be better. It will be a better fit. In fact, the second model is only more powerful because if I set alpha 2 equal to 0, and then I solve for alpha 0 and alpha 1, well, then that's going to give me a linear model again. So the degree 2 fit could be a linear model, but it's able to fit something better. And I've used this technique, right? I've used this A equals the inverse of x transpose x times x transpose y, to get the best fitting model by sum of squared errors, right? So it's clearly going to be a better, smaller residual, but it's not doing something too crazy, right? And then the degree 3 fit one, the fit seems to be about the same, but I know I have an extra aspect of my model that doesn't seem to be very useful. Although it's probably, if I keep following it to larger and larger x values, it's probably going to head back up again. So maybe that's good. So maybe it's a mix of both. The degree 4 one is going to eventually come back down. The degree 5 one, I believe, is eventually going to come back up again, or maybe it starts up off extrapolating beyond the data. And then this degree one is probably overfitting. So yeah. So the right way that we're going to kind of mathematically approach this is what this first comment is saying, is that we're going to try and see how well, and think about how well this does on new data. Okay, new data we haven't seen yet. Okay, and built into this assumption is that the data is going to be roughly like the data we've seen, right? The data is drawn, we're going to say the data is drawn IID from some unknown distribution. So this is telling us a couple things. One, the data we have is a good representation of the unknown data, but also we probably shouldn't worry too much about this extrapolating factor. Okay, so the new data we're going to see is probably not, we're probably not going to get data outside of this range here. The new data is probably going to be in the space of the data we've already seen. Because we're drawing IID from some unknown distribution that kind of involves the X in some way, although not entirely. I mean, this is kind of a gray area in the mathematics, but we should think of the new data as being kind of similar to the old data. Now, this idea of worrying about extrapolation beyond where we've seen the data, this becomes much messier in high dimensions. In 1D, this is very clear. Where is the range of the data? We can say pick the interval between the first and the last point and say that's the range of the data. In high dimensions, this is a really weird problem. And you could think of like a convex hull of the data in high dimensions, but that might not be a good representation. And so we're probably gonna be extrapolating there to some extent, but this is gonna be much harder to quantify. So there's another comment about the third one has a good balance between the bias and the variance. So this is an interesting point. There's potentially some bias here in the choice of the polynomial model. Possibly. This is not totally clear. Basically, all of these models, once you fix the polynomial degree and the type of model you're going to do, these are all going to be effectively unbiased estimators with respect to if we assume the data is going to keep coming from the same kind of distribution it's currently coming from. It's treating the data as having the X value is exact, and think of there's some kind of Gaussian or normal noise on the Y value. And if you look at these models, and this should be true on all of them, all the ones except for this weird eighth one, right? That there's going to be some points above the line and some points below the line. And those should roughly balance each other out. Okay, so all of these are going to be unbiased models, actually. If you get into the next section in the book, which we're not going to cover in this semester, is about where you add bias into these models, and there you're kind of balancing bias and variance. We aren't adding any bias at this point, so we're basically finding the best model with zero bias. It turns out adding a little bit of bias, you can actually reduce the sum of the bias and the variance, which is the overall error on new data. But we're not going to get into that. That's a cool thing if you've heard about that. But you'll have to wait until the data mining class that might be mentioned in the machine learning class as well to kind of think about how to exploit that there's a bias and variance going on. We're just minimizing variance. So we're actually, this is the minimum variance minimum variance solution. And the bias is actually going to be equal to 0. Okay, so the variance, remember, is the expected value of the squared distance from the mean. And if we're assuming we're hitting it exactly, we're kind of we have error on both sides because residuals could be positive or so negative, the best solution will be something like an average, and that'll have error on both sides. And then the squared residuals is basically the difference, is like the squared error from the expected value, and that's going to be like a variance. So we're finding the minimum variance solution. Yes. Okay. Good. Good. So this is a great way of thinking about it. So let's go a little bit more into this idea that our goal is to make good predictions on new unseen data. Right, so that's basically going to be our goal. In the way we're phrasing these regression models, the same for classification. This is basically any supervised model where your data has an x value, which is the explanatory variable, and the y value, which is the dependent variable. Then you want to predict well on new data points where you only see the x and you don't yet try and see the y, right? So this is where we're modeling as we want these residuals. And this is again why we're phrasing the residuals in this way of let's say of the model alpha of xi minus yi, kind of the absolute value or the square of the residuals. This is what we want to be small. We want the square of them to be small on average, right? And so that's kind of, if we did not have this yi, we want it to be close to it with the model, right? So that's what's going on here. So this concept is called generalization. We want the model to generalize good to new data. Okay, and so with the degree 8 fit I showed in the previous slide, it's working well on the existing data, but we would guess that it probably would not do good on some new data, right? If I get a new data point, say, which is going to be, say, where's a guess a new data point? If I got a new data point right here, right, where I put it right where the bump is, well, it's right on this line, right, in between these two old data points. You think, okay, a model should be able to do pretty good on that, but the model decided to make a big jump there, right? So that's kind of, it's not necessarily doing good on if that's where you might expect data to be, right in the middle between two other data points, but the model is not necessarily going to do good there. Where if I looked at this model, well, it's hitting right on there, right? To look at the same point in these other models, it's going to tend to do better. Okay, so that's a good guess, good indication it might not be generalizing well onto new data. Okay, so this is what we'd like to do. The question is, how can we actually use our data, use what we have, the data and our types family of models, to try and estimate if it's going to generalize well to new data, right? We've used all our data to build the model. Any of the data points, well, the degree 8 one is doing the best on the data points we have. So how do we do this on some new data? So if you're a very kind of untrusting person, okay, may not untrusting, but maybe you say like a very skeptical person, then you could go and so collect new data and then try on this new data and kind of see how well it's working on this new data. So you say, okay, here's going to be some data, go and build a model on this, and then we'll see what happens, right? So there are there's a bunch of these models about like these like presidential elections, and there are some analysts who collected things like, how's the stock market doing? Have we been in a war? And they built this model that on the last 10 presidential elections, it was able to predict who was going to win or something kind of like that. Said, well, how is this going to do on like the next election? So, well, you have to wait for the next election. It's not useful after the next election. You might want to know before the next election, right? So it's not necessarily useful to wait to try it on new data. Sometimes you can do this, right? And you're not kind of, training, you're not somehow cheating on the data you have. But if you can't wait to collect new data, then what should you do instead? So the kind of other way of doing this is to save some of the data for testing. Okay, so if I think I'm not going to get any new data, the data I have is what I have to work with, and I want to know how well it's going to do, or I want to choose this best parameter, and the right thing to do is to save some of the data. Don't take some of the data and put it aside, and don't build the model on it, and use that just for this evaluation part. So okay, so let's kind of formalize this. Okay, so we're going to think of having some data, and I'm going to draw it in a particular way. This is X, just to kind of be clear what's going on here, because there can be some kind of conceptual mistakes that are easy to make if I'm not clear about this. And so this is our data. And we have, if you remember, we have this underlying assumption that each xi, yi is iid from some unknown distribution. Let me call this f, right? Maybe there's some, it's an observation, but we represent it conceptually as a random variable, perhaps, if you want to analyze it. But it's drawn, each row is drawn iid from this distribution. And so think of this guy here as being some row. This is xi, and this is yi. Each of these rows is going to be, we conceptually think of as iid. This was the foundation for how we got to use sum of squared errors, right? We want to get an average over the data points, and if there's some Bayesian inference assumption with normal noise, and then you have to, this is part of the assumption to derive that. Okay, so if we think this data is all iid, then we can say any of the data we see is a good representation of new data we haven't seen yet. Okay, and so what we'd like to do is take some of this data and put it in this test set, hold this out for a test set. Okay, and we're going to randomly sample some of these rows. Okay, I'm going to randomly sample some rows. Okay, and I'm going to put some test set down here. Y test, and these are these rows here. Okay, and so there's this, I'm just randomly sampling these into these spots here. Okay. So this is kind of, so I'm going to hold out these data, and then everything else. So all of this other data I have left over. Okay, this other data here that I did not choose to be in the test set, that's going to end up here in my training set. Right, and that's going to go into here. Right, so that's this data here. Okay, so I've split my data in test set and train set, and because it's all ID, if I pull out a sample, this test sample I've held out, then this is a good representation of what I think new data would be like, because new data would come from this same distribution that I haven't seen yet, right? So if I get a new data point, right, then I want my model to do well on a new data point from F that I haven't yet seen yet. So okay, great. So okay, so once I have this, then I need to kind of be careful. Just to be explicit, I'm going to do training on this. You know, I'll do something like this is on the training data, right? So I'm going to build a model. My model alpha is going to be built just on the training data, right? So this model is built only on the training part of the data, not on the testing part of the data. So if I had those 8 data points before, maybe I have 5 data points I'm doing training and 3 data points I'm keeping for testing, and then after that I'm going to do an evaluation where I'm going to model the sum of squared errors, right, which is going to be on X test, Y test with the model from the train. Okay, so this is going to be the sum over I equals 1 up to n test, right? In this case, there are 5 blue lines I've evaluated here, right? Or maybe I'll write this as xi, yi from x test, y test, right? And I'm going to evaluate the model from alpha train on xi minus yi squared. Okay, so this will be my evaluation. The testing data I've held out acts as data I haven't seen yet, and it tells how well did the training process work. Okay, and so this gives me this gives me a value. This is equal to the sum of squared errors. So okay, and so if I want to guess how well will work on new data, okay, so what I want to do is I want to do 1 over the size of X test, right, times the sum of squared errors on X test, Y test, alpha train. Okay, so what's going on here is I'm saying I'm going to use this model I've trained on the training data, and then I'm going to evaluate it on this test data. This is exactly kind of this expression here. Oh, I don't. So I want to evaluate it on the test data, use the model, the training data, and evaluate on the test data. And then I'm dividing through by the number of the test points, right? So if I have 5 testing points in this small example, I'm going to get a sum of squared errors, the sum over 5 points, but the average squared error is just dividing by 5. So this kind of gives me a sense of when I divide through by the number, that gives me a sense through by the expected kind of squared error I'm going to get. Often you do the root squared error, so it's acceptable, or to do the root of this, and then it's going to be an actual, it's more like a standard deviation instead of a variance. Okay, but I'm getting the root mean squared error. So with this would be the root mean squared error, where the divide through the yellow part, the normalization is going to give me a mean squared error instead of the sum of squared errors, and then the root makes it back to the same scale as the original data. But this gives me a sense of how well I will do, how accurate I will be on some new data. And this will allow me to generalize, to predict how good this model is. Okay, so is this, yeah, so I'll go through a small example in Python today where we'll work this out explicitly on actually the same data I showed the example on. It's not always that you do a random split. Let's not use pink there. So I've randomly held out data here. And do you actually need to randomly hold out data if you assume the data is IID, right? If I assume they're all independent from the same distribution, right? That means IID. Do I really need to randomly split it? In the homework, you're not going to randomly split it. So there's less randomness in your answers, and it's easier for us to grade when we eventually ask you to do this. So in a lot of cases, you'll see in some evaluations, they don't necessarily randomly split it. They'll just take the last few data points as the data that's being held out here. I think it's a good idea to often do to take them randomly, to randomly hold out some data. The reason why is the data might effectively be IID from some distribution, but sometimes it's pre-processed before you get it. It may have been sorted. If it's stored, maybe you take the data and you store it in a data structure or a database, and maybe it's sorted alphabetically by name or numerically by zip code, just the way it's stored. So when it's output to you, it's somehow stored it in some way. And then if you take just the bottom ones, that might not be an unbiased sample anymore. So I think it's generally good to probably try and take a random sample when you're holding out some data. Okay, that's not always done, and for simplicity, you won't in the homework, but I would recommend always randomly trying to hold out your data. Maybe that just means randomly shuffle the order of the data points and then take out the bottom ones. Okay, but if you're not 100% sure of the origin of your data, it's probably good to randomly try and pull out the test set here instead. So okay, so let's yeah, what was the next thing I want to say? So so how large? So yeah, let's talk about how large should the test set B. So so in the previous example, I said I pulled out like 5 out of about 15 points, right? But what's the right fraction to try and try and pull out? So it's common to so it's common for test size to be something. So having 10% of your data is common. Having, say, 33% is common. So these are kind of common things between the test and the train split. So why would you? I mean, but if you have 100 data points, the difference between 10 and 33 of them is like a pretty big difference. So what is the right answer here? So the answer is there's not like one kind of right magical answer here. So the right way to think about this is that you're trying to evaluate the expected value of the error by so averaging so n test of these observations. Okay, each of these observations should be an independent and IID observation given the model you have. Okay, so it means we can kind of think of applying the central limit theorem here. Okay, or these concentration of measure bounds if you want to go kind of and try and quantify something. And right, so if we get one view of it, well, it's a sample from the distribution, so might be an unbiased estimator, but we only get one view. All right, if we want to get more views, we're going to get a better estimate. These are going to concentrate, and basically it's going to be unbiased, and the variance goes down by the variance divided by n test, right? So basically what we know about the central limit theorem is that it's going to give us an unbiased estimator of the error that we're generalizing, and the variance of that error is going to go down by a factor of n, or the square root or the standard deviation, the square of the variance is going to go down by a factor of square root n with the number of samples. So kind of how large should it be really depends on how much accuracy do you think you are trying to get in your estimate. Sometimes it's more important to put kind of information into the training, so you're actually getting doing a better job training on the data, right? And sometimes you really care about really knowing how well this is generalizing, and so you actually really want to know, you want to get a very good estimate there at the end. So you want to save more data in the test set because understanding the generalization properties is more important. And if you think the model is more complex, something more complex is going on, maybe your initial variance is higher, right? So if you try just something on a trial with a small subset of data, and it seems like the errors have a lot of variance in them, then you might not be holding out enough of the data because you're not getting a very good estimate because you still have a lot of variance in these errors, right? So it's more of a control of how much data can you spare. If I have like millions and millions of data points, right? We now have these enormous training sets for learning about text or these images people have collected. Then you have lots of data you can hold out, but that also means that maybe only 1% of the data is already giving you a really good estimate of how good your error is. But then there are also these approaches which are really fine-tuning the models. So you're building these really complex, deep neural network models on something, and you really want to see which one is better. Well, to do that, you need more training data. Otherwise, you can't really distinguish them. If the difference between how well the models is doing is smaller than the standard deviation, then you can't really say one is better than the other. Okay, so it's kind of this trade-off. And yeah, 10 and 33% are pretty reasonable values if you have lots of data, but where is it in there? Generally, as you get more data, if the variance doesn't grow, the number of points you need in the test set stays the same. So you can use a smaller percentage of it. Okay, but as your data gets smaller, you might need to hold out more data to get a good sort of evaluation. Okay, so general rule of thumb is more data, less test size, but also more complex model, then you want more test size. Okay, so if you get more data, you need less. I mean, it's not size. I should say. Actually, this one is size. The less tests say a percentage. So a lower percentage of the test data do you need with more overall data. But as the model gets more complex, you might need more test size, which means you might need a higher kind of fraction of the data. So if you think that's really a high degree polynomial fit, then you might want to hold out more data because you think there's something complex going on. There might be a lot of variance depending on where the data falls. So okay. Okay, so now an important conceptual point I want to highlight is, so I've said this 2 or 3 times, but I just want to say it clearly on a slide. So what is cross-validation used for? Okay. So what is the use of cross-validation? Okay, so the first thing is to see how a model generalizes to new data, right? So this is what we talked about explicitly, right? If I divide through by the number of test points, I could see basically what is the expected squared error on some new data I haven't seen yet, right? So let's see how it generalizes onto new data. But then we started out the lecture with something different, right? Started out with these 6 or 8 different models with different polynomials we used to fit data to. And so I could also say, well, given which one generalizes better, that's what the one I'm going to select. To select a parameter in some parameter in the model, and so the example is P in right. So if I choose the polynomial degree of the model, what I would do is I would hold out some data. I would train each of the different parameters under some, on the training data, I'd create 8 different of these models, and I'd see which one did best on the data that I held out, right? So I would do that P star, which is the best, would be arg, so min of P in 1 up to 8, right? If I went up to a degree model here of sum of squared errors of x train, y, x test, y test on m alpha to this degree p. Okay, so I would build these 8 different models, and this is, so I'd build eight different models. So here I'm going to train 8 models, and this is going to be to choose the best. So I'll choose the value p. Maybe in this case it was like 2 or it was 3, right? In the examples we had, 2 or 3 seem to be the one that generalized best onto, maybe one of those would generalize best onto new data. Then I would choose the model that used that degree p. So I would choose the degree 2 model because that seemed to get the best score, the arg min, right? The minimum score with that model that, based on the test data that I, which I held out, then I would choose that argument, right? Arg min chooses the argument of this. I choose the value p. Okay, so I can choose the best parameter doing this. Right, so these are the 2 uses. It's not to try and minimize the sum of the squared errors, right? I have a different process that does that. This is trying to predict how well it does on new data, or to change, or to choose this this best parameter. Okay, so now I want to emphasize another point, not both. Okay, I don't want to do both at the same time. Okay, it's important not to try and both assess generalization and to select the parameter at the same time here. If I do this, if I choose, right, I'm doing some arg min process here, right? This process, it's an arg min. Arg min kind of looks like, we took, this Bayesian inference thing, and we wrote down the maximum a posterior estimate, or the maximum likelihood estimate, and then we took the negative, we turned it into a minimum. We found the minimum cost function, right? The function which minimized this error, right? That was kind of selecting our model. And then we did that again here. We chose the value p star, which minimized the model. We're again optimizing a model here, just in a discrete way instead of a continuous functional way. So this is also building a model. So we don't want to use this same result to say how well it generalizes, or we're going to overfit again in the exact same way. Right. So question: Can you do both if you have 2 test sets? Yes. Good. So you can do both if you have 2 of these test sets, right? So if we go back to this picture, right, we're going to have, what I'm going to do is I'm going to select some data here to be my test. So this is going to be this is for my testing, and I'm going to use this to choose parameter, and then I'm going to go and do this again. I'm going to select a different subset of the data. Typically, you do this without replacement. I'm going to put these down here, and I'm going to use this data to evaluate. I'm going to use this data to evaluate generalization. Okay, and then everything that is left, right, is going to be up here, which is the training data. Okay, let's see. Hopefully, I've got enough. So okay, so if I do it in this way is okay. This process is okay to choose the parameter and to evaluate the generalization. So so now you can think of this whole upper part here as being the training of the model, right? So the whole upper part with the train and the top test set, often this stuff is like often called the dev set instead, and then you have the eval set at the end. Okay, then this process is actually okay. So so this point is kind of subtle. It's often missed, but this came up about 5 years ago. There are some pretty kind of public things that happened where there are these kind of challenges put online through like Kaggle, right? They post this experiment where they post data. Kaggle will say, here's a challenge, here's some training data, go and try and train a model to solve some sort of problem. Use any technique you want. Once every day, you can go and send us your model, and we will evaluate it on the test data, and we will tell you like how well you're doing. And then they'll post a leaderboard of the people who are doing best on this leaderboard, who've done the best on the test data, right? And they say that the contest will close after so many days, and whoever does the best actually wins. And so some people realize this issue with this, that you can actually learn what the test data is by throwing random models. Okay, throw random models at this test server. And then you can do these like ensemble techniques in machine learning, which we're not going to cover in here, but you can kind of take the average of these techniques and they will generalize really well in the test data. So then on the last day, you run an ensemble method on all of those really random models you threw at it, and you can do really good on the leaderboard on this last day. So they've kind of often really well-run contests now. What they do is they provide the trained data, they allow you to ping once a day into the test data, and then at the end, they have this separate evaluation set that they evaluate all of the best models on. Right, so because otherwise people could actually spoof these challenges. They could effectively learn the test set by making these probes by trying to train these random models. Okay, so you have to kind of split this in this way if you want to do choose the parameters and to evaluate the generalization. Okay, cool. Let's see what else. I want to go through the example. Let me leave 5 minutes for that. Okay, I just want to say for 5 minutes, let me tell you some kind of I think, useful side information and some recent developments. So if your data is so small, then you actually are worried about using your data in the test set. Then you don't want to waste data on test, right? So I was on like the committee of someone who's doing their PhD, and they were doing some stuff. They were analyzing these brain scans of some people who had some, it was an accident or something, and there were ones where they had managed to get a before scan before they got in a car accident, and then they took one afterwards, right? And then maybe they took a third one later on to see how they recovered. But you can imagine most people have not had their brain scanned. They don't have like an MRI of their brain just on file in case you get in an accident. So they only had like 10 data points. Okay, so they didn't want to waste it by holding out 33% of the data points. They only had 10, and there's lots of variability. It's a very high variance thing. But they had this, and this data was like a really precious resource. No one else had this data. What can they do with that? And so they often related to more of these statistical models where you assume something about the noise. And they didn't use cross-validation as much. They often kind of did this hypothesis testing view of the world where it said, let's assume this model and then let's test against it with only 10 data points and see if it holds up. The other thing that they did is leave one out, cross-validation. Okay, and this is where you split your data set into pieces where it's like where each time the test set, so the test set is of size 1, but you try all. So I do it this way, but then I'm also going to try it like this, and I'm going to try it with this one, which is a different one held out. And then I can take the average of these. Okay, so this is more expensive. Now, if I have n data points, I have to train my model n different times on all subsets of size n minus 1. I only get one thing to evaluate, but I actually do 10 evaluations, so I can then average those. Okay, so this is more common to do on very small data. It takes longer, but if your data is small, it still doesn't take that long. So it's going to be okay. Okay, so this is something you can do on very small data. And then again, you'd probably just use this for generalization. If you want to publish a model, you'd still probably train on all 10 of the data points. There's other versions of this where you do cross-validation, 10 cross-validation, where you hold out different 10% of it and then take the average of these. And maybe this is a bit better. Okay, so there's a variety of variations on these. Okay, I want to talk to you about one cool, new development. And this, this is called the double descent. Okay, so there's this idea that the model complexity. Okay, as your model complexity, think of like as a proxy for this, think of as the polynomial size p. Okay, and think of this as the error. Okay, and on your training data, as the model complexity goes up, the error is going to go down. So this is the training data, right? As I can fit a more complex model, I can do better on the training data, but on the test data, evaluation data, it's probably not doing as well. And at some point, it's going to go back up. This is on the test data. Okay, and so then you probably want to choose here, right? You want to choose where the test data is at the bottom. And so this area would be, so traditionally called overfitting. Okay. So this has been the view for the, I don't know how long, like 40 or so years since people have been doing cross-validation and polynomial regression. This is what I basically told you so far. It turns out that in certain cases, if you add so regularization and have lots of data, then something else happens. Okay, then what actually happens is that you come down, it starts to go up, and then it kind of goes down again, and you do even better. And this is on test data. Okay, and there's this is called the double descent because the test data does better and then it does better again. And this threshold is often called the interpolation. So threshold, where basically, this is basically where P is equal to N. P is equal to the, in our example, the number of data points you have. Okay, and at that point, there's only one model which can possibly work well. Okay, after that, if I'm just doing polynomial regression, it turns out that the parameters is bigger. If I look over here, like in this side, the parameters is bigger than the number of data points I have, and I try and invert the matrix, it doesn't actually work. Okay, so so I need to add some regularization term, which you can read about in the book. We're not going to talk about in this course. Talked a lot in the data mining course, but that kind of allows you to still take the inverse, and it kind of says it's like adding a prior onto your model, where this is like a maximum likelihood model. Adding a regularizer is like doing the maximum a posterior model. That's one way to think about it. If I have a prior, then what happens is, as I fit a more complex model, it tends to go, that test error tends to keep going down. And this kind of plot showed up in a paper just 2 years ago where they showed this in a bunch of different settings, and now it's showing up all over the place. In fact, this is why when deep learning kind of started making these breakthroughs about 5 or 10 years ago, people are very confused. They're like, they're overfitting to the data. Their model was way more complex than the number of data points they had, but they were doing some things which are implicitly regularizing the solution in some way. And that was causing it to do this thing where it was, again, once it got past this interpolation threshold and the models were complex enough, then it started doing even better on the data. Okay, I don't have time and I haven't gone through enough of the background to really explain this to you, why this is the case, but this is kind of a really cool, very new insight from like 2 years ago, and I want you to be aware of it. So when you think about kind of overfitting, maybe overfitting doesn't necessarily happen if you add some regularization in here. Okay, so in the last 5 minutes, I want to switch and do something on Collab, just show you how this works. And then I can take some questions on this or anything else. So, and share again. Okay, great. We're back here again. Okay, Okay, I can't see. All right, okay. So let's go through here. We're going to use just NumPy and matplotlib to plot some stuff. This is the same data set I showed you initially, but now I've effectively randomly split it into the test and the training set, right? It gets the X and the Y values, right? And so I've colored the test set in blue. You know, on plot I set it blue, and the training set, or the training set in blue and the test set with an E in green here. Okay. And so now I'm going to use this polyfit function, which is going to give me just this array of coefficients, and I can evaluate it. There are other ways to do this, but this way kind of abstracts the how I do the evaluation, so I can more easily write the same code for different values of p. And I start with p equals 1. Can measure the sum of the squared errors on the test set, right? So I did the fit on the training set. This is the training set, I did the fit, but I'm evaluating on the test set, right? So I put in the test X and I compare to the test Y. That's residual. Here's the residual on those 3 points. Some are positive, some are negative. And this is the sum of squared errors, 5.86. And I can plot this. And look, here's the line. And sum of squared errors, 5.86. Okay, let's try this again with a different value of p. With 2, retrain it, and plot it. Okay, my sum of squared errors went down to 0.91, right? This looks like a much better fit. You can see on the green points it's doing better. Okay, try with degree 3. Refit here, 0.93. Okay, slightly worse. Let's look at the picture. Okay, they look about the same. If the score is about the same, I should probably go with the simpler model. If this had been slightly less, if this had been 0.90 instead, I still probably should have gone with the model of 2 because it's simpler. And but this is worse. So model of 2 seems worse. Let's try 4. Degree of 4. Now I have error of 3 again, above 3. And so on this point, which is outside of the training data, right, it's really extrapolating here, then this point is probably giving me most of my error. Right, and let's try again with 5. 5 now, I think, I may only have 5 or 6 training points. Let's see if I can. So 33 is my training error, and let's see what it looks like. Oh gosh, right? This one is probably it's measured this vertical error in the y distance, and it's probably predicting something which is negative here. So this one's probably giving me a lot of problems. A residual of -5 just for this one point, right? Squaring that is like 25 or maybe 28 or something, right? Let's try to see if I can go up to 6 here. Oh, it says there's some warning from rank. Yeah, I tried to invert something maybe that I shouldn't have. And look, I fit a model. It's actually slightly better somehow, but it's still bad. Okay. So I can train these different models, evaluate them on this test set, and this is part of the training. And I would say, okay, degree 2 is the best. This has my smallest error, and it's the simplest model. And I get, okay, good. Yeah, so again, this should be linked off of the web page right here. So you can click on that and try that yourself. You know, play around with stuff, put your own data in there. Maybe for the homework, you'll be asked to do something kind of like this. I forget if it's, yeah, I think it should be on the next homework. You'll do something kind of like this, and you can see how it goes. So, okay, so if I had split the data differently, I may have gotten a slightly different result. You know, we can assume that these were done randomly, but you know, I made sure I chose them so I got a result that actually made sense, because that's what you're supposed to do if you give a lecture. But you know, if you split them randomly, this is only like only 9 data points here. So this is, this was created to make it to work. You probably want a pretty simple model if you only have 9 data points. Okay, so I'll stop there, and happy to answer any sort of questions, and I have my office hours. So